Continuing with our solution to the problems faced in commutation, we'll be today discussing. We have already discussed the brush shifting method. Today we'll be discussing the second method, that is commutating poles, or what are also known as interpoles. So as we have discussed with the brush shifting method, there are issues and these issues need to be addressed. So the brush shifting method was actually used very long back and is now restricted to very small DC machines. But in larger machines, we go for the other two methods that I have listed already, the interpoles and the compensating winding. Now, first discussing the commutating poles or the interpoles. As the name itself suggests, is interpole, so it is somewhere located between the poles. So the idea of commutating poles, or shortly it's also known as compoles or interpoles, is to basically make the voltage zero in the wires that are actually undergoing commutation. Fine. We will make voltage zero in the wires that are undergoing commutation. So those wires that are actually at any moment going commutation, induced voltage in them will be made zero, and with voltage made zero, the sparking problem, that was actually the issue caused by increase in voltage along the brushes, will be removed. So we will actually be able to remove the sparking problem, even the flashovers, by making the voltage zero along that plane where the brushes are actually located. So what do we actually do here is we make use of small poles, which are known as commutating poles or interpoles, and these small poles are placed between the original main poles. So on either side of the main poles, we'll be placing these small poles, and that's actually in between the main poles, the north and the south. We'll be placing another pole, and what will be the polarity of that pole will be discussed here. So these poles will be located in such a fashion that they get placed exactly above the conductors that are undergoing commutation at any interval, so that the voltage so that they also induce a voltage in the so that they also contribute to induced voltage, but this induced voltage contribution by the interpoles will actually be in phase opposed manner to what was the contribution of the armature flux. Fine. So what will happen because of that phase opposition is that the net effect of the armature flux and the interpoles will cancel out each other, and we'll get a zero induced voltage along these armature conductors. Fine. So small poles are placed between the original main poles and midway between the original main poles, and they are located in such a fashion that they are exactly above the armature conductors that are undergoing the commutation. So we actually understand that the armature conductors produce armature flux. The interpoles will also produce a flux. And since the interpoles are basically connected to the armature windings, they are actually connected in series with the armature windings. The interpole will also produce a flux proportional to the armature current. So both the armature conductor is also producing armature flux proportional to armature current, as well as the interpoles is producing uh, its own magnetic field or flux proportional to the armature current. And that means and they will be designed in such a fashion, these interpoles, that they are in phase opposition to the armature flux. Resultant is that the induced voltage will be zero, hence no voltage will be induced and along the magnetic neutral plane, and therefore will cause no sparking on the brushes. So provided actually there is an exact cancellation of the armature flux and the flux produced by the interpoles, we will have a zero induced voltage uh, in those windings that are actually undergoing commutation. But the effect here will be local. This armature flux will be cancelled only in those armature conductors that are undergoing commutation. Everywhere else, the armature conductor that's located, say for example, under the main pole, it will still be producing armature flux that will be actually leading to flux weakening. So this effect is local. It will only make sure that the issue that was with brush shifting and that was with LDI by dt, that was voltage was induced in the armature windings, in the brushes, sorry, at the commutation site, the voltage was induced. That voltage will be equal to zero. That will be the effect of the interpoles. But the second effect, that was of armature reaction, that was of flux weakening, that issue will not be addressed by the interpoles. So let's first of all see how these interpoles are actually connected through a diagram. So here we can see a schematic circuit diagram that basically shows how interpoles are used. As you can see from the figure, the interpole winding is actually in series with the armature winding. So this is your interpole, a small pole that we are placing in between two poles, that is north and south, the main poles. Similarly, if we have a 4-pole machine, then we'll be placing after every pole again, so we'll be having 4 interpoles in that case as well. So you have interpole that's basically placed in between two main poles. So these north and south, that's actually shown here. We now understand actually there is not a magnet being placed there. There is a field winding that actually generates a north and a south. So we are having two interpoles. They are connected in series with the armature conductors, that's with the armature terminals rather. They are connected in series with the armature conductor. So once basically armature is loaded, current begins to flow through the armature. It produces a flux that is known as the armature flux. Now we will be winding these interpoles in such a fashion that since they are also carrying the same current, that's armature current IA, so they will produce exactly the same amount of armature flux. Armature flux will be proportional to the same current. The interpole flux will also be proportional to the armature current. Armature flux will be proportional to armature current, as well as interpole flux will be proportional to the armature current. So as the load is increased, the rotor current will increase. That will actually cause the magnetic neutral plane to shift, and this magnetic neutral plane shift will be dependent upon the amount of loading, fine, as well as there is the effect of L di by dt voltage effect that we have discussed. So both will actually cause increase in the voltage. But now since we are placing interpoles, the interpole will produce its own flux. If the loading is increased, armature current increases, so will the interpole flux also increase. So it will always produce a proportional voltage of its own that will cancel out the voltage because of the magnetic neutral plane shift, fine. So it works with both motor as well as generator. So we are only addressing two issues with this. One is the issue of MNP shift, and second is the issue of L di by dt voltage effect. There is one more effect that is actually caused by the armature reaction, and that is the flux weakening. That is not addressed here because armature current that's flowing at under the main pole is producing the armature flux that will still cause the flux weakening of the main pole. This interpole will have only the effect under for those conductors that are actually undergoing the process of commutation. It will only cancel out the voltage along that commutation site where actually the brushes will be brush and commutator segments basically meet. Now how do we wind these in case of motor? So what we see is, in case of generator, first of all, we see that in the direction of rotation the voltage in the interpole will be of same polarity as that of the pole it has left. Fine. So this pole, interpole, is producing its own flux that will actually cancel out the armature flux only at this location. Fine, you get that. Now how we wind it? This interpole, in case of a generator, in the direction of rotation, it will produce a voltage of the same magnitude in the interpole. That will be actually produced by the magnet, by the pole that it has actually left. That is, it will be causing the same effect that the south pole in this case is causing. Fine. So in order to cancel it out, we need to basically wind the machine. We need to basically produce an armature flux in such a fashion that it will cancel out. So therefore interpole must be of that polarity as of the upcoming main pole. Fine. So in case of generator, say this is pole number, this interpole 1, I will mark it as I1, and this is interpole 2. In case of generator, I1 and this is the direction of rotation, omega. In case of generator, I1 should be producing north pole, and I2 should be producing a south pole. Fine. In case of motor, it will be the reverse. If this here a motor, I1 should be south and I2 should be north. Fine. So basically what we see in case of a generator, in the direction of rotation, the voltage that is actually induced by the interpole will be of the same polarity as that it leaves. Therefore, to cancel it out, we need to basically wind the interpole in such a fashion that it basically has the polarity of the upcoming pole, that is north in this case. Fine. This is for this case. Now it may not always be north here, it can be south here and north here. Then in that case I1 will be south, this will be north. So you have to remember it that I1 should be of the polarity of the upcoming pole. I1 should have polarity of upcoming pole. In this case you can write I1 should have polarity of leaving pole. Leaving pole and upcoming pole, this is basically dependent upon the direction of rotation. So we have discussed this issue, and with interpoles it will basically deal with the issue of voltage induction caused by the brush shift as well as by the magnetic pole shift and the LDI by dt voltage effect. It will not address the issue of flux weakening. So therefore what we basically see is interpole is actually used in almost all the DC machines and of rating 1 and horsepower or above. Fine. Now to address the issue of flux weakening, we use compensating winding. So what do we have here? We basically use a winding which is known as a compensating winding, and this winding is basically placed uh, in slots that are actually carved in the main pole faces, fine, parallel to the rotor conductors. This here is your diagram. So what I said, we basically place the windings, uh, we basically carve out slots in the main poles, in the main pole faces, and in that windings are basically arranged that are parallel to the rotor conductors. So this way we can basically address the issue of flux weakening under the main pole faces as well, fine. In case of interpoles, that was only addressing this winding slot of the armature, but these armature slots were not addressed. So what we have to do is we have to address the issue of other armature slots as well, the flux produced by those armature slots and for that we are using compensating winding. The windings are similar to interpoles. These windings are basically in series with the armature conductors. They are also in series with armature winding. So again they will be carrying the same amount of current that the armature carries. So armature current flows to the armature winding, it produces an armature flux, but the same amount of current will be flowing through the compensating winding as well. It will be producing compensating winding flux. Now these windings are basically arranged in such a fashion that if the direction of current at this end is outwards, the direction of current in this end will be inwards, fine. We are placing them in series, but in such a fashion that they will be carrying current opposed to that of the parallel armature conductors. So this way they will basically produce a flux. So we can actually show that. I'll be showing armature flux here. This will be the flux produced by the armature. It's in this direction, and this will be the flux produced by the compensating windings, and it will be in this direction, fine. So what happens is that the compensating winding will produce a flux component that cancels out the armature winding flux. So the resultant will be if this is your MMF of the pole, of the main pole, fine, this is MMF of the main pole, this is MMF produced by the MMF produced by the rotor, this will be the MMF that will be produced by the compensating windings, fine. This is MMF produced by the armature windings, and this here represents your MMF produced by the compensating windings. So net MMF will be summation of 3 MMFs, and you can see that the MMF produced by the armature windings and the MMF produced by the compensating windings cancel out each other. So the net resultant will be only the MMF produced by the poles, the main poles of this machine. So this compensating winding basically allows us to address the issue of flux weakening caused by armature reaction by cancelling out the armature flux entirely, fine. But it has some disadvantages as well, even though this is the most uh, among all these techniques that we have discussed, the brush shifting, the interpose, the compensating winding, this may seem to be the best, but it has its own issues. One, it is expensive because we have to carve out slots in the main poles as well, and then place compensating winding in each and every pole. So there will be, so normally a DC machine will be having 50 armature slots, so you'll be having almost uh, 40 to 50 compensating windings. You will be having 40 to 50 slots for compensating winding as well in the main pole, carved out in the main pole. Fine. So it is expensive, and secondly does not cancel LDI by dt effect. So LDI by dt voltage effect will still remain there. For that we need to use interpoles. So what we do is, in even larger machines, what we do is we use both interpoles as well as compensating windings. So this way we can address the issue of armature reaction. Armature reaction causes two issues. One is the brush magnetic pole shift, and second one is the flux weakening, and we have also the issue of LDI by dt voltage effect. So these ways, the interpoles and the compensating windings together, they can be used to cancel out the effect of all these three. Fine. But you need to now remember, interpoles will affect magnetic pole shift and LDI by dt voltage effect, while as compensating windings will actually be used for flux weakening effect. Fine. So this finishes our discussion on problems in phase-10 commutation on DC machines.